Okay, now let's see another example. I have G defined as equation 12 and H is 1. I have unit feedback system, so H is 1. The loop transfer function again would be G, and then I can find the loop transfer functions poles and zeros. I have a pole at the origin, one at -4 and two at -4 plus J4 and -4 negative J4, and I have no zeros. So we have 4 poles and no zeros. The number of poles is more than zeros, hence the number of separate loci is 4. If I place them on the map and then I try to find out what part of the real axis is in the locus, I realize that -4 to 0 is in the locus. Let me show you. So I place these poles here and I realize that -4 to 0 is in the locus. Now, if I put the arrows on the locus, it's clear that I have something coming out from this pole and also from this pole. So they meet somewhere in the middle. I can find that point in the middle using the breakaway points, but I don't know what happens to the locus that comes out of this pole, and I don't know what happens to the locus of this pole. And I need four separate loci or four lines in this map. Okay, so this is an example that includes everything we have studied here. So I know the segment that is in the real axis. I plot poles and zeros, and I realize that we have asymptotes. Why do I have asymptotes? Because I have breakaway points, and because I have four different loci, they probably at some point go to infinity. So I use the equations to find location of an angle of asymptotes. I find out the location to be -3 and the angle to be 45 degrees, 135 degrees, 225, and 315 degrees. So here, right? So there are gonna be four loci that follow the asymptotes. So the location of asymptotes is here, and then I have angles defined like this. Okay. Now clearly they cross the j omega axis. How would I find the location of where they cross the j omega axis? Well, I can use Routh-Hurwitz criterion or Routh-Hurwitz table to find what value of k the loci would cross the j omega axis, and then where is the location on the j omega axis that they cross. So I write down the characteristic equation, use Routh-Hurwitz table, and then I find that this is the k, this is the value of k, and the exact location that they cross the imaginary axis is plus minus 3.2. I can also find the breakaway points. I can invert GH, or in this case just G, and then take the derivative of it and put that equal to 0. It gives me three answers: -1.5, -3.7, plus minus J2. Which one is in the answer? Which one is the acceptable answer? Only -1.5 is the acceptable answer. These two doesn't really make sense. Let's see. Is it possible that somewhere here my poles meet each other? No, at -3, -3.7 plus minus J2.5. No. It makes sense though for the poles to meet at -1.5. So here, right? Because these two poles are moving towards each other, they have to meet somewhere between 0 and -5. Okay. So I found the breakaway points. And the last item to calculate is the angle of departure from the pole at -4 plus J4. So I want to find the angle of departure from this pole. How would I do that? I can find it via using the formula. I need to find the angle that this pole makes with this pole. That would be just 90 degrees. I need to find the angle that this pole makes with this pole. Again, that would be a 90 degree. And then I want to find the angle that this pole makes with the pole at the origin. It would be more than 90 degrees, right? It's going to be this pole. It's going to be this angle. So I can calculate them and I get 225. This last item is the angle that my pole makes with zeros. There is no zeros, so I just put 0 here. 0 degrees. And this is the finished root locus. Let's see another example. Consider the unit feedback system given in equation 13. The same procedure, I find zeros and poles. I have a 0 at -1 and a pole at the origin and another pole at, I believe, -1 plus minus 2. Okay, plus minus J2. So the only segment that is in the of the real axis that is in the locus is between -1 and 0 if I plot these poles and zeros. Now, so here it would be this. Now I have 2 poles. I don't know what happens to these poles. Maybe I should calculate the location and the angle of asymptotes. If I do that, maybe I realize what happens. Okay, so there are 2 complex conjugate poles that aren't going to cross the real axis. So we want to find out what happens to them. We find the location of the asymptote and the angle. You don't always need to find location and angle of asymptotes, but if you try the equation, it's not going to give you a wrong answer if you don't need any. It's just going to give you 0 or 180 degrees if you have one asymptote going to negative or positive 180 degree. So now we find negative 0.5 for the location and 90 degrees and 270 degrees for the angle of asymptotes. If we calculate the angle of departure from the pole at -1 plus J2, so I want to find this angle because now I know that the asymptote is at -0.5 and the angle of it is 90 degrees and 270 degrees. So I know these 2 poles are never going to cross j omega axis, and I know they never are going to meet each other. There's no point to find breakaway points. So the only thing that is remaining is to find the angle of this pole, right? The angle of departure from this pole. How do I do that? I need to find this angle. I need to find this angle. And then I also have a 0, so I need to find this angle, which is going to be 90 degrees. So 90 degrees, 90 degrees, and then this one is going to be more than 90 degrees. I can either find this angle and add it to 90, or I can find this angle and subtract it from 180, right? So either this triangle is point of interest for me, or this triangle is point of interest for me. And I can use any of those. Okay, so to calculate the angle of departure, I have the formula. I have 180 degrees times 2k plus 1. I subtract from it the summation of all the angle of that pole from other poles, and then I add to it the angle between that pole and other zeros, right? So this is one pole, this is another pole. So I want to add alpha and beta. and then I want to subtract the summation of alpha and beta from 180 times 2k plus 1. I want to add to it gamma, which is 90 degrees. Okay, so this is the math for it. Beta is 116 degrees. Theta is therefore 64 degrees, which is the addition of 90. So you add 180 degrees with 90 degrees. This is the angle of my pole with the 0. And then you subtract the summation of the angle of that pole to other poles from them. We have other examples. I encourage you to read them. They are very similar, and it's all uh, for repetition or for practice. This example, though, is important. So let's look at this example. The reason why this is important is because we have repetition of poles. So if I look at the zeros and poles, I have a 0 at -4, but my poles are -1 plus minus J2 twice. So if I find where on the real axis is in the locus, if I find the number of branches, the location and angle of asymptote, it's all the same way that we did before. I can also determine where the axis crosses imaginary axis. It's all similar. The important part, though, is the last part, when you determine the angle of departure. When you determine the angle of departure, notice that there is a 2 required here. Why do I need a 2? Because each angle is happening twice. So if I want to find the angle of departure from this pole, I have actually twice that happening. So when I find the angle between this pole and this pole, I have it twice. I have this twice. Therefore, I have a 2 theta here. The next topic would be very similar. It's the angle of arrival to a 0. So it's kind of a mirror of what we just talked about. Now you just uh, you have a 0. You want to find the angle of arrival. All the difference between equation 15 and what we had before is that now this is a positive sign, this is a negative sign. So the angle of that 0 to poles now is going to be added. The angle of that 0 to other zeros is going to be subtracted, but the rest of it is similar. Let's see this example. We have now 1 pole and 3 zeros. Okay, so now this is the only example here that we have more zeros than poles. We follow the same rules. The number of separate loci is, so I have 3 zeros, 1 pole. The number of zeros is more, so I have 3 separate loci. And when I want to find the angle of arrival at the 0, remember I add the angle that it makes with poles, and I subtract the angle that it makes with zeros. So now I'm going to have, so I found the angle of arrival to this 0. But the rest of it is very similar. Okay, so to recap, we had Rath-Horowitz and Root-Locus. These are two methods that we use to determine stability. Root-Locus uses the open loop systems transfer function, but Rath-Horowitz uses closed loop systems transfer function and only the denominator. Rath-Horowitz has no assumption on k or gain. It can be anything, but Root-Locus is limited the way we taught it in this course to k being between 0 and infinity. Root-Locus is a graphical tool and shows how poles and of the closed loop system move as we change k. But Rath-Horowitz can only check about stability, cannot talk about performance of the system. And then we have MATLAB examples that you can look at the slides yourself.